In this Soil Slopes and Streams mini lecture, we'll talk about floods and flow. We'll think about what happens when waters get high, how flood processes work, how we study their probability and risk, and how we learn and teach others about the benefits and hazards of floods. Firstly, floods are natural processes. They reflect the conditions of the stream bed, but also the conditions and processes that occur upstream and upslope. You don't need rain at the place you're standing to see a flood, as you can see in this short video. Floods aren't solely driven by rainstorms, and some of the most deadly disasters in human history have been linked to flood bursts from landslide dams. But what is important is that a flood is influenced by whatever happens upstream in the watershed hydrology, and the form of the channel that it is filling and overtopping. Both of these matter. This image is called a flood hydrograph. It shows the change in a river's flow over a time period of a single flood or rain event or storm. There are three different things plotted here, and let's start with the one at the bottom, shown by the series of bars. This is the intensity of rain that fell during the storm. The intensity steadily increased to a peak intensity and then decreased, and the yellow dot is the peak rainfall, the point in the storm where the rain was most intense, and also the middle of the storm in terms of how much rain was eventually delivered. Now imagine the same storm fell over two different watersheds and streams, Stream 1 and Stream 2. Each of these curves that are shown by the blue and green dotted lines reflects the river's respective flow over the duration of the storm. This flow is represented by discharge, the volume of water moving past the monitoring point per time. And here it's in cubic feet per second. Discharge is measured at what's called a gauging station, a point along the river with a monitoring system. Let's focus on the blue curve first. As the rain fell in the beginning of the storm, Stream 1 began to carry more water and flow at a faster rate, which increased until the river reached its highest level and flow. This red arrow at the bottom marks the time between when the storm hit peak rainfall and the river hit peak flow. It's called the lag time because rivers lag in their response. As the storm waned, eventually, so did the stream's flow, until most of the storm water had moved out. Stream 2 experienced the same storm and the same intensity of rainfall, but it was slower to respond than that of Stream 1. Discharge increased with storm intensity, but peak flow followed the timing of peak rainfall with a much longer lag. Stream 2 was also slower to drain, and water was stored in the catchment for a longer period of time. These two different responses, these two different hydrographs, have different names for their shapes: flashy and subdued. And there are a lot of different reasons that these streams might experience the same intensity of rain, but exhibit two very different behaviors. One thing that can influence flashiness is the catchment area. Imagine the two monitoring points for these streams were here on Big Creek and here on the middle fork of the Salmon River, upstream of the junction. Their two watersheds have different sizes, and because of this, the length of water flow paths, both through the hill slopes and channel, are average much shorter for Stream 1 than Stream 2. And so it takes less time for water to flow out of the channel in Stream 1. Other things that influence the flashiness are hill slope or stream hydrology. Variables such as the catchment slope, vegetation both in the channel and on the hills, and the soil type, thickness and whether it can hold much water matter. Geology can also influence water flow because some rocks are less weatherable. Some deep fractures and joints can transmit water through the subsurface. And all of these variables together influence the flashiness or subdued nature of the stream. Urbanization of watersheds can also influence a stream's response to storms. Cutting vegetation and forests to make way for paved roads and buildings reduces the amount of water that infiltrates into the ground. Instead, more water runs off rapidly along impervious surfaces into the stream, increasing the likelihood of catastrophic flooding, such as we see here in the image of the 2009 Georgia floods. But somewhat of a double whammy is that while urbanization can cause faster and higher magnitude flooding during a storm, structures and human changes to the landscape and natural flow paths can also make it more difficult for the water to leave. This means that the floodwaters can remain long after the rains have stopped. There's one added thing that's important in terms of river flow and a storm hydrograph that we didn't cover. It's not well represented in this graph here, but it's what happens at the very beginning and end of a storm and the associated runoff. The green and blue dotted lines that represent these two streams' hydrographs essentially start and end at the bottom of the chart, indicating little or really no stream flow before and after the storm passes. And though some stream beds are dry and only have flowing water during rains, either seasonally or during a single event, many or most streams carry water year-round. This is called the base flow, and it represents the amount of stream flow that's delivered through slow pathways in the soil and ground and from springs. This is not storm runoff. It exists between rains, and it's generally higher for a natural stream or one through a forest than for an urban stream, for example shown as this blue swatch, because impervious surfaces reduce water storage. When a river floods, there's typically a nonlinear relationship between the water depth and discharge. With increasing flow, water stage and depth increase fairly stepwise and rapidly until this inflection point. However, then increases in discharge result in much smaller changes in the depth of the water, a relationship of diminishing returns. This reflection point in the relationship in terms of depth corresponds with the bank of the river. And though depth changes very little beyond this inflection point, what does increase is inundation. This is the overflow and spreading of the stream water across the banks. It's also one of the reasons that floods can be so deadly. Not only do waters rise, but they extend out, even into areas that are far from the channel itself. We can highlight this concept in a real-world example. In 2010, there were devastating floods in Pakistan. Heavy monsoon rains fell across the Indus River basin. In this image, we can see areas that experienced different extents of flooding during the July and August rains. Note how wide an area was flooded and how far from the natural river channel in places. It's estimated that 1/5 of Pakistan's total land area was inundated. 2,000 were killed, but the rivers were also catastrophic for infrastructure, crops, and the livelihoods of tens of millions affected. We're going to zoom into this area shown by the black box to view the river change from satellite imagery. We're looking at 3 images of the Indus River Valley in July, August, and September. These are false color MODIS images from a NASA satellite taken in 2010, And you can see that as the waters rise, they exceeded the banks of the river and inundated large areas. First, we can see the river form and flow at the beginning of the monsoon rains in July was not that extensive. Note the sinuous patterns of what is already a large river. It appears small in this image because of the scale, but to give some sense of the size of this river, here's the city of Soker, right along the banks of the Indus. This will be the region following flooding. Watch as the river floods and waters cover tens of kilometers and waters inundate even further. This image from September shows the amount of flooding at the end of the rains. These waters persisted for months in some places, further hindering recovery.